3, 9, and 1, 7 are linearly dependent. False. How do you know? One is not a multiple of the other, right? You can't take 1, 7 and multiply by a scalar and get 3, 9, or vice versa. So this is false. Okay, so for two vectors to be linearly dependent, one has to be a multiple of the other. Okay, if a homogeneous vector equation, so that word homogeneous, what does that mean? Equals 0. Everything on the right-hand side is 0. Okay. Homogeneous vector equation has only the trivial solution, then the vectors are linearly independent. Independent. That's the definition of linearly independent. That's the thing you can always go back to, because the text offers several shortcuts to determine linear dependence and independence, but this was the definition. So you can always go back to this if you can't find a theorem to help you, or you forget them, right? You can always go back to the definition. All right, if a homogeneous system, meaning 0 is all on the right-hand side, has a free variable, the columns of the coefficient matrix are linearly dependent. Yep. If it has a free variable, then it has more than the trivial solution, which means it's dependent. Only the trivial solution, this you have independent, more than the trivial solution, dependent. Okay, so today we're going to study the concepts of linear independence and linear dependence for a set of vectors. I took a few notes on the reading. So I've been trying to do this a little bit just to sort of give you a template of what it's like to take notes on the reading. So you want to sort of take those several pages and say, oh, think about what is this section about, right? And then just write out the main bullet points. You might have to write out a little bit more to explain these things to yourself, but that's the main thing that it's about. I'll let you just read that over sometime on your own, and we're going to jump right to the demo. So I've got 5 sets here, R, S, T, U, and V. 4 of them you can immediately, or with a little bit of effort, identify as linearly dependent. Okay, so one of the main things from the reading was this number 2, right? The definition of linear independence leads to this important characterization, which is like a description of linearly dependent sets. It says a set of vectors is linearly dependent if and only if at least one vector can be written as a linear combination of the others. So I want to look through these 5 sets, and 4 of them are linearly dependent. So I'm looking for one vector in the set that can be written as a linear combination of the others. So the first one is, oh yeah, explain the first one. Why is that? Because yeah. R is linear, that set of vectors is linearly dependent because I can write 306 as a linear combination of the other 2 vectors, right? So my other 2 vectors are 1, 0, 2 and 4, 6, 0. What weights can I use to make 306? 0 and 3, right? That makes R linearly dependent. If any vector in the set can be written as a linear combination of the other vectors, linearly dependent. Okay, how about S? Yeah, you wrote a question about this, Brendan. It's dependent, how come? Yeah, we have more vectors than there are entries in each vector. That's just a quick shortcut that the book gave us to determine linear dependence. So S, because there are more vectors than entries. So whenever that happens, you're going to be able to write one of them as a linear combination of the other two. And I would just solve a system to figure out how to do it. Should we do that? Let's do it. So you can pick any of the three. Let's say 7, 10, right? Or 7, 10. I want to write this as a linear combination of the other two, 5, 7, and 2, 9. Weights are unknown right now. How would I solve that for x1 and x2? Put in an augmented matrix and solve it. Yep. So let's see, I'll do this on another page. Okay, so we were able to immediately identify this as dependent because of the theorem, more vectors than entries. But the theorem is based on the definition. And the definition says that if I can write any vector as a linear combination of the other two, it's dependent. So if I want to solve this thing, I make an augmented matrix, 5, 7, 2, 9, 7, 10. Row reduce it. And I'm going to show you how to have your calculator row reduce something now. So some of you I showed during the last class, but it's good to make sure everybody has seen it. Okay, so your TI has a matrix button, matrx. Most of them, it's a second function. If you have an older one, it might be its own button. But for me, it's second underneath the math menu, second matrix. So then I have all these matrices, A, B, C, D. I want to edit one. I want to edit matrix A. And the first thing I have to enter is its dimensions. What are the dimensions of this matrix? 2 by 3. 2 rows, 3 columns. So I hit 2, 3, and it creates a 2 by 3 matrix for me. Then you put in the entries. So we've got 5, 2, 7. And then the next row is 7, 9, and 10. So I have matrix A entered, quit out of there. And then you go back into the matrix menu and choose math. So you cursor over to the math menu. Scroll down, there's a whole bunch of stuff you can do with matrices. We want to RREF it for row reduced echelon form. So you hit RREF, go back into the matrix menu. In the names portion, choose matrix A, and then just hit enter, and it gives you the row reduced echelon form. And the cool thing, you can also use 2 fraction to change this. So you can hit math, enter, enter, and you get it as fractions. So this row reduces to 1, 0, 43 over 31, 0, 1, 1 over 31. So now we can move our focus away from the computational aspect of row reducing and just use a calculator. Unless on a test I say row reduce this and show all your row operations, right? So this says that x2 equals 1 over 31 and x1 equals 43 over 31. So I have found 2 weights, right? I have found weights that allows me to write 7, 10 as a linear combination of the other 2 vectors. Right? And when you can write one of the vectors in a set as a linear combination of the others, that means they are linearly dependent. And this will happen anytime you have more vectors than entries. Oops. Yeah. Okay, so we've got R and S done. This was dependent, dependent. T, do we have an obvious way to tell if it's dependent or not? Nothing jumps out at me, right? So I have 4 entries. So if I had 5 vectors, I could immediately say dependent, but I only have 3. If one were obviously a multiple of the other, I could say dependent. But I quickly check and I say, well, doubling or tripling or doing anything, taking any multiple of 0 is never going to give me 2. Right? So I can't, it seems like I can't write 2, 0, 4, 4 as any kind of linear combination of the other 2 vectors. So this one is unclear, right? It might be that I could write one of the zeros as a linear combination of these 2, but that's not immediately obvious. I'll have to do some work. So let's just leave that one for now and move on to U. Dependent or independent? Dependent, how come? It has the 0 vector in it. So I can always write 0, 0, 0 as a linear combination of the other 2 vectors by making the weights 0. So this one's definitely dependent, right? Because anytime the 0 vector is in the set, you can write the 0 vector as a linear combination of all the other vectors using all your weights as 0. All right, how about this last one, V? Independent, how come? Nope. It's dependent, how come? The first 2 added together make the third. Take the weights of these guys to be 1, and that will give you the third vector. Yeah, so for this one, I would say 1 times 2, 2, 2, plus 1 times 1, 6, 9. That gives me 3, 8, 11. So that's dependent. So I think the third one's going to be independent. Yep. So we have to use some method other than inspection because it's not immediately clear whether it's independent or dependent. So I would row reduce it. Yeah, I'm going to take those columns as my matrix 2, 0, 4, 4, 0, 1, 0, 1, 0, 0, 1, 1. Augment it with zeros, right? So I'm setting up a homogeneous system. And if this homogeneous system has only the trivial solution, and that means what? What does it mean to have only the trivial solution? Everything equals 0. Yeah. Then the set is independent. Otherwise, there'll be a free variable and you get linearly dependent. So let's row reduce this thing. Practice it on the calculator. Okay, so I go into matrix, edit, and I want a 4 by 4 matrix. 2, 0, 0, 0, 0, 1, 0, 0, 4, 0, 1, 0, 4, 1, 1, 0. Okay, so I quit out of there. Go back into the matrix menu from the home screen, choose math, go to RREF, go back into the matrix menu in the names section and choose A, and we row reduce it, and I get 1, 0, 0, 0, 0, 1, 0, 0. Okay, so there's my RREF version. Oh, did I? Sorry. Last one's all zeros. Okay, so what does this thing say? Do we have any free variables? No free variables. This says x1 equals 0, x2 equals 0. Sorry, what? Yeah, because you could just see if there was a pivot in every, yeah. Yeah, that would work. Yep. Yep. So this is what we call the trivial solution. So because my system has only the trivial solution, the columns of this matrix, right? These columns are linearly independent. The only way to write one as a linear combination of the other two is if all your weights are zeros. No, that's wrong. We're not talking about that. You can't write one as a linear combination of the other two. All right, that's all I got to show you. I'm going to have you try some.